So why do we need statistics? Okay, so you are learning many other things, so why do you need statistics in addition to that? Now statistics is basically a science of variations. So if someone asks you what is area of a circle, your answer is fixed, pi r square. Then suppose someone asks you what is speed of light, you again give one single answer, 3 into 10 raised to 8 meter per second. Someone asks you molecular formula for distilled water, you give answer as H2O. Now my next question is, what is length of an earthworm? Can you give me one single answer?
No, it will be a range.
It will be a range, right? So whenever you are dealing with such variations, then you need statistics. So if I want to actually study length of an earthworm, what we will do? First, of course, we'll have to take some actual measurements. Okay. And when we take actual measurements, there come the concepts of population and sample. So let me say we want to restrict our study to Pune University campus. So we want to see what is the length of earthworms on Pune University campus. Still, there are lots and lots of earthworms on the campus. So we cannot really go and measure the length of each and every earthworm. That would cost us too much of time and resources. Plus, it could be never ending exercise because new earthworms will keep being born, some will die, and so on. Hence, generally, in any statistical study, we instead of studying the entire population, we take a subset of that population, we call it as a sample, and we study that particular sample. So here we might decide that okay, we will capture 100 earthworms, we'll measure their lengths, and then we have to make sure then we'll get some idea about the lengths of earthworms on the campus. How to choose a sample wisely is another problem. In fact, we discussed this slightly in the cephology example, if you remember. The person who was trying to predict elections, US presidential elections, he got all the predictions as wrong because his sample was not chosen wisely. Okay. So sample has to be representative. So if you just decide that okay, I will walk around the campus and I'll see the earthworms, I'll catch the earthworms if I can see them, then that is not the correct strategy, because all the earthworms that you get in your sample would be the earthworms which are close to roadside. Okay, you may not get access to earthworms which prefer to remain away from the road. So they might have some different characteristics. Okay, they might be shorter, they might be younger, etc., and they might be weaker. So maybe the stronger earthworms only reach up to the roadside, whereas weaker earthworms tend to stay more towards the soil, more towards, I mean, away from the road, etc. So such things can happen. So our sample has to be a representative of population, then only it would be give us good readings. Now suppose this is actually data collected from earthworms. So we draw histogram. So we have now already seen what is a histogram. So we draw such a histogram, and that gives me that okay, possibly 4 to 16 centimeters is roughly the expected length. Majority of the earthworms have lengths between say 7 to 13 centimeters or 7 to 14, but still there are some earthworms which are shorter or longer than this range, and the most frequent observations are between 9 to 10. So most of the earthworms, I mean majority of the earthworms have lengths between 9 to 10 centimeters, etc. Okay, so this histogram tells me something about spread, but this now I need to quantify. So I need to decide what is meant by a normal or a typical earthworm. So we saw here that minimum length is around 4. So if when I use the actual data, the minimum value turns out to be 4.819, maximum length turns out to be 15.179, average length turns out to be 10.055, etc. So these numbers give me some idea about the data. So they tell me, as you said, they tell me at least range. So earthworms are supposed to be somewhere between 4 to 16 centimeters. Then this is the typical or average length of an earthworm, etc. So for capturing such diversity, we need statistics. There is lot of diversity, we need to model that diversity, and for that we need statistics. And another objective of statistics is how to interpret objectively. So this data comes from Norway. So there were incidences of acid rain, and people wanted to study the effect of acid rains on some small lakes, on the pH of water in those lakes, etc. And the period of study was 74 to 78. So they did a small survey of lakes and collected data from those lakes, and these were the variables that were recorded: pH, sulfate concentration, nitrate concentration, and calcium concentration. You could guess the reasons why these variables are chosen, right? How they are correlated with acid rain. Now, this is time series for one particular variable. So time wise plot. So you take multiple readings. First thing is, because you have 74, 75, 76, 77, 78, 5 years of data, you can see almost similar pattern repeating each year. Can you see 5 similar parts of this curve? 1, 2, 3, 4, 5. Because there will be seasonal variation, there will be seasonal changes, right? During the rainy season you might have some values, after the rainy season, just after the rainy season, you might have some other values, and so on. And year to year, more or less, that pattern will remain. So you can see that seasonal pattern here. But if I now ask you, is there an increase in this particular value? So it could be, say for example, pH. So is there a consistent increase in that value across time? What do you feel? Does someone feel that there is an increase, or everyone feels that it's very minor change, it's not an increase? Yes, is there an increase, or is it very minor change? Yes, you have no opinion?
And there's only a minor change.
Minor change, okay. Now let me introduce one more curve. Okay, another variable, this red curve. Now what about red? Can I say that there is an increase here?
Yeah, compared to the black one, there's a larger change.
Larger change. Now I introduce one more complication. So now see the blue one. Now some people might feel that okay, it is more similar to black one, so not much change. Some people might feel that no, it has a change, etc. And there will be lot of subjectivity, lot of debates, etc. So another use of statistics is to decide when such changes are really significant. Okay, so when can I really say that there is an increasing trend and it is not simply more or less similar readings, just slightly higher. Okay, so this is another use of statistics, that is interpreting the changes objectively. Okay, and the very first thing to do, okay, yeah. So first of all, is there any evidence of abrupt change in the values, and if yes, then is that change as expected due to acid rain? Further, we would also like to see if there are any evident correlations among the 4 variables, or among the lakes that are geographically closer to each other, among the values which are recorded with small time gap, etc., etc. Okay, to quantify all these things, we need what is called as summary statistics. So what are summary statistics? These are some numbers which summarize the data in some way, because the data itself will have many numbers, but we will use some of those numbers to summarize the data. So there are two different types of summary statistics. One is measures of central tendency. So measures of central tendency tell me what is the middle value, or what is the typical value, or a normal value in a data. Okay, of course the first one is mean, that is simple average. Then you have median. Median is mid observation exactly at the middle, so it divides the data into two equal parts. And then we have mode is what? Mode is basically the most common observation in the data. So these are known as measures of central tendency. So in the earthworm data, in class 9 to 10 we had highest number of earthworms. So the class 9 to 10 will be said to be it will be called as modal class of that data. Okay, then for an here is an example. Suppose I have data on number of family members. Okay, so a survey was done in many houses, and every house this question was asked: how many people live here? So what is the count of people in your family? So we can see that 8 people said that they were staying alone in their house. 20 people said that there were 2 people in their house. 23 people said 3. 40 people said that there were 4 people in that house, and 9 people said that there were 5 people. So here this value 4 becomes mode of my data. Why mode? Because it is most common. So modal number of family members is 4. Where do you use mode, where do you use median, and where do you use mean? Mean, actually every one of us is familiar. We have always been using mean, even in school days we used to compute our percentage, so that is basically a mean. But there are situations where mean could be very misleading. Okay, for example, suppose I am recording incomes of people or incomes of students who have completed, say, BSc from your department in the past. Okay, now in one batch I recorded their current salaries and I got mean and I got some answer. Now in the next batch, among the 30 students that are admitted, suppose one person is from some very very rich industry family. Okay, so that person gets this degree and gets job in his or her own firm, and suddenly starts earning lot of money. Now when someone asks me what is the average income for this second batch, suppose all the other people are making somewhere between, say, 3 lakh to 7 lakh per annum, and because this person owns a big business, this person starts earning somewhere around 25-30 lakhs in the first year itself. Then what happens? Then when you take average, it might happen that only his income is above average whereas everyone else is below average. So that kind of average would not really be representative. Okay, so in such cases, instead of mean, we feel it is we generally should go for median, because median does not get affected that much by such extreme observations of one or two persons. Okay, one or two observations, extreme observations. And mode is of course useful when you want some general answer like number of family members, etc. Okay, okay so far?
Yes, ma'am.
Yeah. And but we can't simply be happy with just typical or normal measurements. We need to know about the spread also. So that is done via what are known as measures of dispersion. So how do people compute measures of dispersion? So first is simple: range of the data is maximum value minus minimum value, that gives me range. Then there is something called as interquartile range. Interquartile range is q3 minus q1. So which means that q3, we have said q3 is the uh, top line of the box plot. So above q3 only 25% of the observations are there. Okay, similarly q1 is the bottom line of the box plot, bottom boundary of the box plot. So below q1 only 25% of the observations are going to be there. Okay, so this is interquartile range. Okay, another important concept is standard deviation. So standard deviation is 1 upon n sum over x minus xi. Okay, for us standard deviation, so basically standard deviation tries to measure how far away data points are from the mean of the data. So if spread is more, standard deviation is more. If spread is less, standard deviation is less. Okay, then I showed you this type of graph. This is known as positively skewed graph, where you have a peak towards left and a long tail towards right. Okay, negatively skewed graph is exactly opposite of that. So you have a long tail towards left and a peak towards right. So positively skewed data, we saw one example in the earlier graphs, computer usage. Okay, so most of the people use computer for a very small time, but still there may be some people like say programmers etc who use computer for a very long time. Another typical example of positively skewed data is incomes. So most of the people are in these income groups, but there are some Tatas and Birlas and Ambanis here. The negatively skewed data is opposite. So you have a peak here and a very less frequency in these areas. Now, one example of negatively skewed data is age of politicians in India. So majority of the politicians are in higher age groups, and we do have some very young politicians also. Okay, so this is positively skewed data and negatively skewed data. So skewness is one another interesting measure, just like mean or standard deviation. And then another important thing is called as kurtosis. What is kurtosis? Kurtosis again tells me about shape of the data. So this green line is normal distribution, which we are going to see in detail. So it is known to be mesokurtic. Okay, so normal 0 1. So if I focus on this red curve, then in this red curve you can see this red curve is like tall, okay, tall and thin kind of thing, so tall and slim. So this is known as leptokurtic, and the third one is known as platykurtic because it is short in height and hence spread more. Okay, so it is known as platykurtic. Okay, so today I will stop here.